Bismillahir Rahmanir Rahim. Assalamu alaikum. This is lecture number 2 of Fundamentals of Electrical Engineering. Uh, now, since this is the first week of this course, we are still starting this course. And in the last lecture, we talked about the course outline, what we are going to learn. We also talked about some prerequisites of this course. We actually specifically talked about three. One was linear equations, how to solve the system of linear equations. Second was complex numbers. And third was derivatives and integrals. That was our list of prerequisites in the first lecture. Today we are going to do more prerequisites. There are two more prerequisites I would like to discuss. And then we are going to talk about the concept of voltage and current. Now, since this course is about electrical engineering, we don't like to limit ourselves just to these prerequisites. We would like to actually start working on actual circuit concepts, but we must understand that these prerequisites are very important in order to revise the concepts of electricity and magnetism that you have understood in intermediate. Now, uh, there are two more prerequisites. I'm going to first write them here. And the third one last time we did was derivatives and integrals. This time we are going to talk about electromagnetism. There are some things that we need to revise. And finally, today, the last prerequisite we would cover would be some concepts of rotational motion. Now, these two are the topics that we are going to first discuss, and then later we are going to go into the uh, into the concept of voltage and electric current. So let's quickly start with electromagnetism. This is a prerequisite number 4, theory of electromagnetism. Now, what we know about electromagnetism in its very crude form is that there are some natural magnets, some materials behave as natural magnets, and some magnetic lines of forces actually emanate from these sources, and then these lines are called magnetic flux. So these lines are magnetic flux lines, and with this concept there is a notion called magnetic flux. What is magnetic flux? It's a representative, it's a combination of uh, all the magnetism spreading out of a magnet. Spreading out of a magnet. Now, what does that mean when we say it's the combination of all magnetism spreading out of a magnet? It means that uh, there is going to be magnetism spilling in all directions, here, even here, here, all around a magnet. And magnetic flux is the total number of magnetic lines. These are imaginary lines that we consider that exist, and these flow in the space around a magnet, and the total number of such lines is called magnetic flux. So it's kind of the total magnetic energy kind of generated by the magnet. You must understand that. And magnetic flux is represented as and it's represented or drawn as lines that come out of the magnet. Now, the second concept in this regard, let me go to the next section. The second concept in this regard is magnetic field intensity. What is magnetic field intensity? Well, it's kind of the same thing as the magnetic flux, slightly different, but it's kind of the same thing. So, total magnetic energy in a magnet, the total magnetic energy stored in a magnet. Now, this is kind of a potential energy because the total magnetic energy contained inside a magnet is not going to be the energy that's coming out of it. Some energy would still be inside the magnet, and thus the total potential of a magnet to produce magnetic field is called its magnetic field intensity, and it's represented by the symbol H, and it has a unit of amperes per meter. There is another concept that is used more often in magnetism, and it's called magnetic flux density, represented by the symbol B. Now, what is magnetic flux density? Magnetic flux density, here the word flux is important because we already have seen flux. So what happens is that a magnet has total energy inside it. The total energy inside the magnet is its magnetic field intensity. However, some of that magnetic energy is spread into the space outside the magnet, and that magnetic energy is represented by flux lines, magnetic flux. These magnetic flux lines are distributed by a certain amount in every per unit area, and that is actually the magnetic flux density. So how we define it is something like that. When magnetic field leaves the boundary of the magnet, to produce magnetic flux. The magnetism that is available outside the magnet is represented in terms of magnetic flux. Now, this magnetic flux, this whole thing, the number of fields, it depends on the space, how the space, what kind of material is present in that space. For example, if it's air, if it's free vacuum, if it's any other kind of material, that would actually um, magnify, or you can say suppress the amount of magnetic flux. So the material is very important in terms of the spread of the magnetic flux. I should write it here, depends on surrounding material. Now, once these flux lines are spread into the space, uh, they can be, flux lines can be close to each other, or flux lines can be far away from each other. And this concept of close or far away is represented in magnetic flux density. How close are the flux lines, or how close or how far away are these flux lines? So this is the concept of magnetic flux density. It actually depends on magnetic field intensity. So you have seen this formula, B equals mu H, and you can clearly see this is the total potential of the magnetic field multiplied by the coefficient, the permittivity. What is permittivity? Permittivity simply means how good is the material, how good is the space around the magnet, whether it allows the magnetic field to spread or it suppresses or stops the magnetic field from spreading. So the total potential multiplied by how good is the material equals to the actual flux density B. That's what you have in the space that you can measure, magnetic flux density. And the unit for magnetic flux density, B, is the unit here for B is Tesla, or there is another unit sometimes we use is it's called Gauss. We will talk about those units when we are going to do magnetic circuits. They are simply the same units, they have just a difference of a prefix. So Tesla is a bigger unit, Gauss is a smaller unit. We are going to talk about that. And this is how magnetic flux density spreads in the space. There is another concept about magnetism which is closely related to magnetic flux density, and that concept is magnetomotive force. And this is a very practical concept. So, for example, what I'm talking about is called magnetomotive force, or in short, MMF. What is magnetomotive force? It's simply described in this way that, for example, you have this, you know that there is a natural magnet, and in the same way we can create an electromagnet by using some wire and wrapping it around some kind of magnetic material. Magnetic material is a material that supports magnetism, that can become a magnet. So this is some magnetic material, for example, iron. And when you do this and you, for example, connect it to a battery, for example, this, just like this magnetic field from a permanent magnet, this one also becomes a magnet as long as the voltage is provided to the coil. This one is called a permanent magnet. When you are using a permanent magnet, which we use a lot in electric circuits, then the concept of magnetic uh, flux densities it becomes a magnetic field intensity becomes slightly different, and it becomes more practical. So the MMF is described as the total magnetic energy inside an electromagnet and is equal to the number of turns of the coil multiplied by the current. So let's say this is the current flowing in the coil, I, and N is the number of turns, the number of turns that you have wrapped the coil around the magnetic material. So MMF is the same thing, is the same measure as magnetic flux, magnetic field intensity. It's kind of the total amount of magnetic force present, but this time MMF is much more practical. It's used in practical electromagnets, and it has a very simple formula that you can easily measure for any coil. You just need an ammeter and you just need to count the number of turns. Moreover, let me revise you some basic magnetism laws. The first one is these are simple laws, you know them, but let me revise you for the sake of brevity. So you understand magnetic field of a current carrying conductor. You know about that. Every current carrying conductor has a magnetic field around it. So let's see what if you can recall this from your past learning. So for example, you have this conductor and it's placed in open space, and let's say some current I flows into the conductor. It goes through the conductor, goes through all the way and comes out the other side. So this current is flowing. You must remember that this current is going to produce a magnetic field, and for our case, the direction of the magnetic field would look something like this. On every point of the conductor, there is going to be concentric circles of magnetic field lines going around the conductor, and they are not going to be one line, they are going to be concentric, so there are going to be more lines at every point. Their radius would be larger and larger, and the further they go away from the conductor, they would become weaker. So this is how uh, the magnetic field looks like when a current flows in a conductor. This is how it looks like. How do you how do you get the direction of the magnetic field? You can easily find the direction of the current using an ammeter. Once you have found the direction of current, you can use the right hand rule. And let me draw it in kind of a diagram. I'm not really good at this, but let me draw it for you. So for example, this is your right hand, and this is the conductor that the current is flowing through. And your thumb, this is your thumb is pointing in the direction of the current, and then you grab the conductor with the help of your fingers. So let me draw some fingers here. This is the first finger, index finger, the second finger, the third finger, the fourth finger. And this is how you grab the conductor. And you can see if your thumb is pointing in the direction of the current, then the curl of the fingers, this is the curl of the fingers are curling around the conductor. This curl is going to represent the direction of the magnetic field. This is as simple as that. Apart from this, there is another similar kind of thing in magnetism. You have seen that, and that thing is uh, the magnetic field created by an electromagnet. How does it look like? So for example, you have created a magnetic field, for example. So magnetic field of a solenoid electromagnet. Now, we are talking about solenoid shaped electromagnets. So for example, this is your piece of iron or metal that you use to create a magnet. And this is a wire that I'm going to wrap around this magnet. So it goes around the back, comes in the front, and then again goes in the back, comes in the front, goes in the back, comes to the front, and then again goes to the back and comes all the way out. And I am using some battery to provide current to this coil. And you know that some current is going to flow here. This would be the probably the direction of the current. And if you trace the direction of the current on this coil, you can see it goes like this, goes and turns around, goes to the back, comes from the back, and here goes like this in the front, goes all the way to the back, turns around, comes in front, now it's over here, again goes to the back, all the way comes over here, and this is the direction. So you can see the current direction in the coil. That's quite easy to do. The question is, how would this magnet behave? Would this be the North Pole or would this be the South Pole? This is the question. So how to answer that? It's quite simple. We again use the right hand rule. And the method of doing it is this, that you take your right hand, for example, this is the coil. You take your right hand, let me draw your hand. Obviously, this is not your hand, but looks kind of like it. So we are going to, this is good enough for this course. This is not an art course, so this is good enough. So you take your hand and then you bring your hand on the coil and curl your fingers around so that they are in the same direction as the direction of current. I repeat myself. You take your hand, you put it on the magnetic coil, and since you have already known the direction of the currents, you curl the finger of your hands in such a way that they are in the direction of these currents. When you do that, your thumb would be pointing in the direction of the magnetic field. So let's do this for this coil. Now, for example, so if I want to do this here, let me first draw this coil again. This is the coil. And we would like to uh, know the direction of the magnetic field. We know the direction of the current. You can see that the direction of the current here in this coil is going like that. Now bring your right hand and you put your fingers in such a way that they are in the direction of these currents. This is your thumb, and now your thumb is pointing towards the magnetic field, and hence we can say that this is the North Pole because the magnetic lines are leaving from here, and this is the South Pole as they are entering over here. So this is another interesting idea, how to know the orientation of your electromagnet. Another very famous idea here is the force idea. Now you know that when there is a magnetic field and there is a charged particle, there is going to be some force induced in that particle. And we know that we have learned about that in intermediate. So let's talk about it quickly. The next idea in this prerequisites revision is that, for example, for actually the idea, let me put the idea first. The idea is the force induced in a current carrying conductor inside a magnetic field. And I would need to draw a really nice diagram for this. Let me quickly draw it. I'm going to be vocal while drawing. So for example, this is a current carrying conductor. Oh, this conductor is not the one I need. Okay, even this one is bad, but let's just talk about this. So for example, this is a current carrying conductor. This is a piece of wire and it can conduct, and you know that the conductor is placed inside a magnetic field. So I'm drawing the magnetic field over here, and let me suggest the direction of the magnetic field. It's this arrow. So lines are coming from here, from left to the right. This is the magnetic field. And a current, let's say I, is flowing into this conductor like this. It's coming out like that. So this is the situation. Whenever this situation arises, uh, there is going to be, let's say we are talking about this point. So at every point on this piece of conductor, there is going to be a force induced. We can drive a formula for one point, and then we can multiply the length of the whole conductor to that. So let's say if this one point we want to find out the direction of force, how this conductor is going to move in this magnetic field, uh, it's quite simple. And the method is simply to use the right hand rule again. And how to place your right hand this time, it's slightly tricky. So for example, I'm placing my right hand. First of all, you need to make sure that the fingers of your right hand are pointing in the direction of the magnetic field. You can see the magnetic field is in that direction, and all the fingers are pointing in that direction. And it's very logical because the field has many lines, so you have many fingers and you can point those in that direction. Secondly, your thumb. Your thumb need to be pointing towards the direction of the current. You can see it's almost like that. So it's pointing in the direction of the current. Now, let me clarify. This right hand over here, with its fingers pointing in the direction of magnetic field and its thumb pointing in the direction of the current, is actually you are looking at the back side of this hand. So there are your knuckles. Your palm is on the other side of this diagram. If you put your fingers in this way along the magnetic field and your thumb along the direction of the current, then your palm is going to actually into the page show you the direction of the force. So in this case, in this diagram, the force is actually into the page. However, you know that since the magnetic field and the current which are producing this force, and they are both uh, actually 90 degrees apart, this is actually a cross product. So the formula for force is actually this. You already know this from your previous learning, that I L cross B. L is the length of the conductor, the direction of the length is the direction of the current, B is the magnetic field intensity, magnetic flux density, and the cross product of these two is going to give you the magnitude of the force. Or simplifying that, we write F is equal to B I L sine theta. This is the magnitude of the of this force. So this conductor is going to actually start moving into the plane of this diagram. This is how you identify the direction of force on a current carrying conductor which is placed inside a magnetic field. There is another very important law about magnetic field induction, and that is the Faraday's law of electromagnetic induction. And that is this next thing that we are going to talk about. So what is this Faraday's law? You might already have studied this, but let me just quickly revise it for you. So Faraday's law of electromagnetic induction, what does it say? So let me just quickly erase this line because, okay, that's better. So Faraday's law of electromagnetic induction. What this law is about? In this law, if you want to understand it, you need to first understand uh, the idea that um, when you have a magnetic field, whenever a magnetic field interacts with a conductor, uh, it induces a voltage in the conductor. Actually, the equation is very simple. You have might have already seen the equation that E, which is the voltage induced, the induced voltage in any conductor which is present in a magnetic field, is equal to minus n d phi by dt. We are going to talk about this equation in a moment, but you, I think, realize this, that this is an equation that you might have seen before. This is Faraday's law of electromagnetic induction. Now let me explain this law. So, for example, you have this coil. You just make a coil out of a wire, and in order to detect the current inside the coil, you use an ammeter or a galvanometer. So this is ammeter or galvanometer. You connect that to the coil, and now you use a simple permanent magnet like this, north pole facing the direction of the coil. You know that magnetic lines are coming out of it, and you start moving this towards the coil. Note that I'm saying you are moving it towards the coil. What's going to happen when the magnet move? The answer is, if you do this experiment, you would observe that there is going to be a clockwise deflection of the needle of the ammeter. Here, the needle is going to go in this way. This is what's going to happen. If the magnet moves towards the coil, there is going to be a current, and that current would make the ammeter needle go clockwise. So there is some current in one direction when you move this magnet in one direction. When you move this magnet, let's say now in the second time you are going to move it away from the coil. So magnet moves away from the coil. When you do this experiment, you're going to see that this time the ammeter needle has a counterclockwise deflection, and that is going to uh, tell us that there is some current, but this time it's in the opposite direction. So in the first time it would be going in this way. Sorry, let me use the right color here. Well, in the first experiment, when the magnet was moving closer to the coil, the current went that way. Now when it's moving away from the coil, the current is going this way. And third and last, and a very important observation is that when magnet is stationary, no current flows. This was the experiment that led to the Faraday's law of electromagnetic induction. And the equation of the Faraday's law of electromagnetic induction says that, let me write it here, there is going to be some voltage induced in a coil. So this is voltage induced in a conductor or a coil, and that voltage is going to be equal to a negative sign, we will talk about it in a moment, times the number of turns times the rate of change of magnetic flux. So very important thing over here, there needs to be a time varying magnetic field. Only then you would get some voltage. And by the way, this is the same law that is the basis for the operation of generators, and that is the basis for the operation of transformers. So if there is a time varying magnetic field, then there is going to be some voltage induced in that coil. In this diagram, we talked about current because current detection is easier. But let me show you that if we used a voltage over here, for example, if we connected a voltmeter over here, then we would see the same phenomena. One time the voltage would be in one direction, the other time the voltage would be in the other direction. One important thing is, what is this negative sign doing? And this negative sign is due to Lenz's law. You know that when the magnetic field from the permanent magnet is coming to the coil itself is going to produce a magnetic field which would oppose the incoming magnetic field. This is a slight detail into this topic. We would talk about this detail when we would be learning transformers, and I would be talking about Lenz's law in much more depth in the topic of transformers. So until then, you need to understand that this negative sign is due to Lenz law, and it tells you that the reaction of the coil is going to produce a magnetic field in the opposite direction. And that reaction magnetic field is not over here in this equation. This equation only talks about the action part of this phenomena, the law of electromagnetic induction. By the way, there is an interesting idea. In this case, we used a permanent magnet over here. You see, if you move this magnet closer or far away, some voltage is going to be induced in this direction or in that direction. However, we can do the same thing by using another coil. And in the second coil, we are not going to connect it to a battery, but instead we are going to connect it to an alternating voltage source. In this way, the magnetic field of this coil would also be alternating. And since the magnetic field is alternating, the rate of change of flux that comes from the first coil to the second coil is also alternating. And hence, we get an alternating voltage at the output. So by replacing the permanent magnet and connecting the permanent magnet, by replacing the permanent magnet with a coil and then connecting that coil with an alternating current source, we can produce an alternating magnetic field. And that magnetic field, since it's alternating, is going to produce an alternating voltage. This is actually the basis for transformers, how transformers operate. I am not talking about the transformer robots. I'm talking about the transformer that is present in many of your home appliances. So this is one more thing that I wanted to discuss, and then finally there is another concept. This is the fifth prerequisite I wanted to discuss with you guys, and that is some concepts of rotational motion. Now, this concept, there are many concepts of rotational motion. You are particularly quite familiar with them, but I'm going to talk about basically two concepts very quickly. Now, consider this example. Let's say this is a motor, and this motor has a shaft, and shaft has a pulley, and on the pulley, at the very end of the rim of that pulley, there is a piece of string, and there is some mass m attached to it through that piece of pulley. So there is a weight pulling that pulley downwards. Now, if I start the motor, let's say the pulley starts rotating in this direction. Assume that it's going in this direction. This is the angular speed, and this is the radius of the pulley. You must understand the concept that there is going to be a torque applied on that pulley. You know the formula for torque is R cross F. In this particular case, R is simply R and F is simply the weight downwards. Remember that the radius and the string, the force that's pulling the string are both 90 degrees apart. That's why the cross product is going to be written like this. You can say R cross W is actually mg, and if you want to know the magnitude, then it's going to be R mg sine theta. Sine theta is nowhere here because sine theta in this case is sine 90 degrees, which is 1. So this is the torque on the shaft of a motor. That's one concept that I wanted to revise. Another concept is that the angular speed, you know, that is for any motor or any machine is omega, and it's represented in radians per second. However, in this course, we are not interested in this unit. We want a practical unit, and electrical machines have a better unit to measure their speed, which is called RPM, revolutions per minute. How to convert omega into RPM? So RPM speed, it's simply, you can do the conversion yourself, but I am just going to write it for you here. It's 60 over 2 pi times omega. So you put in the angular speed in radians per second multiplied by this factor, you are going to get the angular speed in revolutions per minute. So this is it for today's lecture, and thankfully, all the prerequisites have been ended. You need to practice these prerequisites. I'm going to be putting quizzes and problems relating to these prerequisites also in your classroom. Apart from these, we are going to talk about um more prerequisites when we come to the specific topic. But for now, this is good enough for revision. This is the end of this lecture. Inshallah, in the next one, we are going to talk about voltage, current, power, energy, and formally, we would be starting the course from the next lecture. Thank you very much. Keep informing me. Keep giving me feedback about these lecture series, about the quality of audio and video. If you are able to understand the concept and the English spoken here, please rate these lectures. Thank you very much. Inshallah, in the next class, we will be formally introducing electric circuit concepts. Allah Hafiz.